Hello, this is the 4.4a trapezoid notes. Start off with the definition. A trapezoid is a quadrilateral with exactly one pair of opposite sides parallel. If we were to have two pairs of opposite side parallel, we'd have a parallelogram. So this is just the one where we have one. So in this case, we have side SR is parallel to side XV. As with all of our recorded videos, feel free to pause the video at any time. That way you can write down what you see. I also do provide blank notes along with the video. Okay, moving on to slide number 2. Parts of a trapezoid. The parallel parts of the trapezoid are called the bases. Okay, and the base could be vertical like this, horizontal like this, or the parallel sides could be vertical. Okay, it doesn't necessarily have to be, because it's called a base, it doesn't have to be the bottom. All right, but we do call the parallel sides the bases. The sides that are not parallel are called the legs. All right, these are called the legs. So again, it could be oriented differently, but the parallel sides bases, non-parallel sides legs. Angles. The angles that are made up, okay, we have a pair of green base angles. All right, these are the ones that go with along the side SR, and then we have some red base angle pairs that go along the side XV. Okay. You have a right trapezoid if you have a trapezoid with a pair of right angles. Okay, now that pair would be on different sides. All right, so we have a pair of right angles here, one on the side that goes along with KL and the other that goes with side MJ. That is a right trapezoid. An isosceles trapezoid is a trapezoid that has a pair, okay, of congruent sides. Those sides would be the legs. All right. We'll actually use isosceles trapezoids quite a bit because they involve some more properties than just the general trapezoid. You'll see some properties that we remember from parallelograms that creep in here to the isosceles trapezoids. First theorem for trapezoids. If a trapezoid is isosceles, then each pair of base angles are congruent. All right, so remember, base angles pair up along the same parallel side. So angle P and angle A would be congruent. Angle T and angle R would be congruent. All right, this is where we get our paired up parts here. Okay, and this is similar to like a congruent triangle or an isosceles triangle. All right, if we had an isosceles triangle, the angles across from those congruent sides are congruent. Same idea here. You've got your congruent legs, all right? Well, the angles across from them are going to be congruent. Now, you got to be along the same base. So along PA, two congruent angle pairs, or along TR, two congruent angle pairs. Okay, so here's a kind of an example of a problem we could have here. Given that ABCD is an isosceles trapezoid, find the measures of the remaining angles. Okay, well, there's a couple properties we know about all quadrilaterals. Okay, we know that all quadrilaterals are going to add up to 360 degrees inside. All the angles will add to 360. All right. We also know that in this isosceles trapezoid, base angles are congruent. So if B is 63, so is angle C. All right. Now, one thing we didn't talk about, but we also could think about these legs. Think about the legs as being transversals. Okay, because we know that these bases are parallel. So this is like a transversal, and we can actually use the fact that these are same side interior angles. Angle D and angle C are same side interior angles, which makes them supplementary. Okay, so if I do 180 minus 63, that's 117. That's going to be angle D. And because it's an isosceles trapezoid, this angle A, which is also a base angle pair with D, is also 117 degrees. Okay? So we can find these remaining angles a couple different ways. We could have added 63 and 63 together, subtracted from 360, and then divided by 2 to get these angles up top. But I like using this method. If you know that in any trapezoid, whether it's isosceles or not, if you use that leg as a transversal, you will have same side interior angles, which you can then find that angle that goes along that leg on the opposite base. Okay? Another theorem. This is kind of the reverse. If a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So what we had before is we were told it's isosceles, therefore the base angles are congruent. In this example here, or in this theorem, we're given angles that are congruent. That proves that we have an isosceles trapezoid. Okay, it's kind of the same way. We had a similar theorem with our triangles. We had both ways where we said if you have the congruent angles, you've got a congruent sides. If you've got the congruent sides, you got the congruent angles. It goes both ways. Another theorem. A trapezoid is isosceles if and only if its diagonals are congruent. Okay, so this one is, we're bringing back this is a very similar theorem to what we have with our rectangles. Okay, where the diagonals were congruent. Now the difference is in rectangles, all 4 segments were congruent. In trapezoids, the diagonals are congruent, but you're going to get 2 different pairs of congruent parts here. So these small pairs are going to be congruent, and these bigger segment are going to pair up and be congruent. Okay? So, but again, together you have a single and a double hash, a single and a double hash, so the diagonals are congruent fully from TA and RP. Okay, this covers all of our definitions and theorems we'll be using with trapezoids. If you need to, pause the screen right here and write these down. Hopefully you got them all along the way though. There is one more part that we want to talk about with our trapezoids. That is the mid-segment. The mid-segment of a trapezoid is a segment that connects the midpoints of the legs. So this is drawn incorrectly, and I keep saying we need to correct this every year, and we don't. I'm just going to make these doubles as well. All right, so connects the midpoints of the legs. So if we had a leg, TP, the midpoint would be right here. It would make TM and PM congruent. Okay. And S is the midpoint between R and A. If you have a mid-segment, okay, that connects both midpoints of the legs. So point M and point S were in the midpoints. That makes this the mid-segment. Now there's some properties that go along with the mid-segment. The mid-segment of a trapezoid is parallel to the bases, and its length is half the sum of the lengths of the bases. Okay? Now, the parallel part's easy in this, okay? The part where it says its length is half the sum of the length of the bases, another way of saying that, it's the average length of the bases, okay? So if you were to add the bases together and divide by 2, you'd get the length of your mid-segment, all right? But that's one way of talking about it. It's the average length between both bases. So if I wanted to find the length the length of MS, which is our mid-segment, okay, I could add the 2 bases together, 12 plus 34, and divide it by 2. Well, 12 plus 34 is 46. 46 divided by 2 is 23. Okay. Now, one way to look at this, 23 should be halfway in between 12 and 34. So 12 plus, what is that, 11? 34 minus 11. Okay. So it's directly in between. It should be right in the middle. which is what average is. Okay. Here's one where we're trying to find the length of PA. We can do this a couple different ways. I think the most straightforward way, I'm going to do the same thing. 13, what do I have to add to 13 to get to 27? I add 14. Well, guess what? If I add another 14, I should get to the other length, PA. 27 plus 14 is 41. Okay. And if I were to just double check, 13 plus 41 is 54. 54 divided by 2 is 27. Okay, so that does work. Now, another way to solve this one is instead of doing this, I can make this a variable and I could solve an equation. Okay, I could do x plus 13 divided by 2 equals 27. So you add the bases and divide by 2 to get your mid-segment length. Well, I multiply both sides by 2 to start. I get 54 equals x plus 13. Subtract 13 from both sides. We get x equals 41, which is what we got the first time around. Okay? So it works either way there. Find two possible lengths for the bases of TRAP. So just we're trying to find the two possible base lengths. The key to this one, I know that the average of these two lengths has to be 15. Okay, the average of the two lengths has to be 15. So what I can do is I can double 15, which is 30. I just need to make sure my two lengths add up to 30. Okay, all you need to do is add up to 30. So if I do 30 and 1, or 29 and 1, so let's say it's not drawn to scale. That's a length of 1. That's 29. 1 plus 29 is 30. 30 divided by 2 is 15. That works. Okay. We could do the only one you can't do here is 15 and 15, because in this case you'd end up with a rectangle. Okay, because these lengths would both be the same, which would make them perpendicular, and it'd be a rectangle. So the only one you really can't do here is 15 and 15. But if I went 14 and 16, that would work. Okay. All you need to do is pick any two lengths that when you average them, you get your mid-segment length. You can also have a problem where you're solving for a variable here. We could do 2x minus 7 plus 7x plus 11 divided by 2 equals 20. Multiply both sides by 2. I'm going to combine my like terms as well. 9x plus 4. Subtract 4 from both sides. And divide by 9. X equals 4. Okay. Again, pause this if I'm moving too fast. I'm trying to make the video not terribly long. All right. Given that WXYZ is an isosceles trapezoid, okay, I'm going to go ahead and mark this so I know. And the following data, find the length of WY. So our goal is to find this diagonal length. Okay, let's write down what we got. WQ is 3x plus 9. XQ, let's see, XQ is 5x minus 11. And QZ is 14. All right. Now, in an isosceles trapezoid, we know the diagonals are congruent, and we also know that the small segments are congruent and the big segments are congruent. Well, there's an equation we can use to solve for x. 3x plus 9 equals 5x minus 11. Subtract 3x from both sides, add 11 to both sides, divide by 2. I get x equals 10. Okay, I get x equals 10. Now, I need to solve for the length YW, okay, or WY. Well, if I can solve for XZ, that'll be the same length. So I'm going to go ahead and plug 10 in right here. 5 times 10 minus 11. 5 times 10 is 50. 50 minus 11 is 39. And if I add these two segments together, 14 and 39, let's see, 53. This length is 53, so WY is also 53. Okay. If you can find one diagonal length, you found the other if it's an isosceles trapezoid. Okay. Given, these are the last couple are just some problems that you could have with trapezoids. Given ABCD is an isosceles trapezoid, find the measure of angle DBC. So we're trying to find DBC, this one right here. Okay. Now it's isosceles. This is going to help us out. We know that's isosceles. We can do this a couple different ways. All right. Now, one thing I'm going to do, I know that this angle is 112, so I know the big angle up here is also 112. One thing I also know is I have a triangle here. And if I know the full angle is 112, if I can find this angle there and subtract it from 112, it should leave me with angle DBC. Well, let's do that. Let's add 112 and 31 together. 143. We're going to subtract that from 180 because I know this red triangle, all the angles inside have to add up to 180. It's going to be 37. So this angle right here is 37. So to find DBC, I'm going to do 112 minus 37. This is Mr. Newberry not being able to do this in his head, so he's going to go old school. 5. That's 75. Yeah. So we got a 75-degree angle here. Okay. All right, I think we got one more. Given that TRAP is an isosceles trapezoid, find the measure of angle TRA. So we got TRA. All right, so this is the angle we're looking for. This one's pretty straightforward. If we add these two together, we should be able to get this one. Okay. Tell you what, I'm going to switch this problem up around. We're not going to find TRA. We're going to find the measure of angle TAP. All right. We're going to find TAP. So we're actually going to try and find this angle right down here. All right. Now, we can not only can we use the legs as transversals, but we can use the diagonals as transversals too. So this angle TAP should be congruent to this one. They're alternate interior angles. Okay, because this is the transversal, the diagonal is the transversal. Our top and bottom sides are the bases. So this should be 21 degrees. Okay. Now we could have done that original problem, but all we had to do was add 47 and 21 because this top angle is equal to this top angle. We know they're congruent. All right. So I wanted to do something that involved another transversal because I don't think that we recognize those as quickly as we should a lot of times.